Good day, everybody. This is Chris, the Ancient Scholar. Hope you all doing well. Hey, I wanted to go ahead and do a quick video covering the nerve agents, and I'll actually be doing a series of videos. I'm doing some videos where I'm working with some molecular exercises, and I'm doing voiceover. It may take a bit of time though, because I'm going to be doing a fair amount of editing there, so there may be a little higher production quality there. So what I want to do now is I want to talk about the major weaponized nerve agents, and these basically fall into what are known as the organic phosphorus classification of agents. I've talked about these in a little bit of detail in earlier videos, but I'll just go ahead and show you some of the basic molecular structures of some of these. So you basically have, within the organic phosphorus weaponized agents, you have two types. You have what are known as the G type and the V types. The G types are really the prototypical weaponized nerve agents. G means German, and the way that it works is that the NATO code is actually a G followed by another letter, and the way that it works for nerve agents is GA is the very first of the weaponized organic phosphorus agents that was created. And then GB was the second, GD third, and then GF fourth. And those are the four prototypes, if you will. And then the V agents came a little later on, VX, of course, being the primary one. Now, all of the nerve agents share a basic central structure, and that is the organic phosphorus structure. So you have a phosphorus atom, and that atom is going to be attached to carbon somewhere, carbon, and of course it may be attached to oxygen as well. So some people call these organophosphates, but as you can tell, this is not a phosphate, right? It's not, the phosphorus isn't, like a PO4 or something like that. In this particular molecule, you can see the phosphorus double bond to an oxygen, oxygen, carbon, and a nitrogen here. So clearly this is not a phosphate. So I prefer to use the term organic phosphorus, but a lot of people will use the term organophosphate, and in a practical sense, they can be used synonymously. So I suppose there you go. So what I have here is an example of the very first weaponized nerve agent that was developed in the Germans, I believe in the late 1920s. Maybe a little later than that, but certainly, yeah, the kind of the early part of the century there. And this is something known as Tabun, and this is the first agent, so this is known as GA. It goes by the NATO designation of GA. You can see that it has the central or organic phosphorus structure to it. So I have my phosphorus atom, I have a double bond to oxygen, and in all of your potent agents, your highly potent nerve agents, this particular bond right here is very important. When you have a phosphorus and a double bond to an oxygen, that makes for a highly toxic agent. There are other types of nerve agents, like the carbamates, for example, which is something that I'll talk about a little later on. And the carbamates do not have this structure. They're not nearly as toxic, and some of the carbamates actually have to be metabolized into a metabolite that has a structure for them to be toxic. So this is a really important structure here, this double bond to the carbon, or to an oxygen atom, excuse me. Okay, so here I have it. I have a triple bond carbon nitrogen here. I have a nitrogen that comes off. This is the leaving group here. Two methyl groups. I have an oxygen, a carbon, and a methyl group that comes off the carbon. And you'll just kind of have to imagine that there are hydrogens where there need to be hydrogens, for example, right here. But that's a basic structure. It can interact. You have this nonpolar area here that can interact with the nonpolar part of the acetylcholinesterase molecule. You have more of this polar part here that can interact with the different residues, the serine residue, and that. And actually, what happens is you have a bond that occurs between the phosphorus area and the serine residue, and that's what blocks the acetylcholinesterase receptor. So Tabun is a pretty light, has a molecular weight of about 162 grams per mole, thereabouts. It's pretty simple, as you can see. Its melting point is pretty low, about -5 Celsius. Boils at about 240 Celsius. And its volatility is about 600 milligrams per cubic meter. So it's fairly volatile, has a fairly low melting point, so it's really easily found in a liquid form. Its volatility is reasonably volatile, so it can volatilize into a vapor. So your primary hazards with this are going to be skin hazard, vapor hazard. Taboon's kind of colorless, maybe a slight brownish color, kind of a really faint fishy odor. And obviously, if you're at the point of being able to smell it, there's probably going to be a problem. Onset of symptoms are going to be really quick, seconds to minutes if you're talking about inhalation, maybe up to a couple of hours if you have skin absorption. The LD50 for this particular agent is, you're looking at skin, about 100, maybe up to 200 milligrams of absorption. The LCT50, the lethal concentration for inhalation or skin exposure, is going to be around 200 to 1,000 milligrams, thereabouts. All right, so there we have this particular agent. So now what I'm going to do is I'm just going to modify this slightly. What I'm going to do is I'm going to see if I can do this while holding the camera. We'll see. So I'm going to take the nitrogen and the two methyl groups. I'm going to just pull them off. And I should have just pulled this bond off with them, but we'll see how that works. Okay, so what I'm going to do is I'm going to pull them off, and I'm going to replace them with a fluorine atom here. Okay, there's fluorine. And then I've got this group here. I'm going to replace this group here on the side, and I'm going to replace that group, put these off to the side, with a methyl group here. Okay, so some fairly easy, fairly basic modifications. All right, let me just put that up and out of the way there just to, okay, so there we go. And then what I'm going to do is I have the oxygen here and I have the carbon. I'm going to have the methyl group here. And then what I'm going to have is I'm going to have another methyl group that comes off of this. Oh, Lord. All right, well, you just have to use your imagination. there's a hydrogen there that popped off. Okay, so there we go. So I added a fluorine group, methyl group here, methyl group here. All right, this molecule is a molecule of sarin, okay? And sarin is Gb, so it was the second agent. As you can see, we've lost some atoms, so sarin is actually going to be even lighter, about 140 grams per milliliter. Its melting point is much lower, about -56 Celsius. Boiling point about 158, and the volatility for this thing is about 20 to 22,000. Highly volatile. Okay, so this is not going to remain in liquid for very long before it evaporates. So its primary route of exposure, if you will, is going to be primarily inhalation because it's so volatile. So it's not going to stick around as a liquid. It's not going to be a very persistent agent at all. Sarin or Gb is colorless, may have a real faint, kind of a fruity kind of odor. Seconds to minutes for its onset, and its lethal pharmacological properties are pretty similar to taboon. It is, I think, it's pretty similar. Okay, it's going to be pretty similar. Okay, so now what I can do is I can actually modify this molecule a little bit, and what I can do is I can take this carbon and these methyl groups off, and I can attach a aromatic ring to this guy. Let's see if I can actually do this one-handed. I don't know. Maybe. All right, so I have my aromatic ring here, and because I'm kind of limited on time today, you're just going to have to imagine that I have a single double bond, double carbon bonds, and you can fill in the hydrogens wherever they go. But there you go. Okay, so I attached a aromatic ring to that molecule, and this creates an agent known as GF, or cyclosarin. Basically, I've just added a cyclic ring to the sarin. Okay, so I have an aromatic ring to the sarin, And cyclosarin is going to be a little heavier than taubeun and sarin and GAGB. Similar to taubeun, about 180 grams per mole for its weight. Pretty similar. Its melting point is going to be fairly low, about -30. So it's basically in between taubeun and sarin. And its pharmacological properties are going to be more or less similar to, its physical properties, its volatility is about 438, 440 right in there, so it's a little less volatile than taubeun and not nearly as volatile as sarin. You'd expect that with this big old benzene ring hanging off of it there. Its pharmacological properties, it's roughly similar. It's not nearly as toxic as taubeun, sarin, or soman. Soman is D. I haven't talked about soman yet, but it's not quite as toxic as those three, but it's fairly similar. Let's see here. Cyclosarin kind of has a sweet, fruity odor. You know, you've got your aromatic ring, so that doesn't surprise me too much. Its onset's going to be pretty similar as well. And then there is also an agent known as a soman, which is GD, and soman basically you go back to your sarin molecule, you add another methyl group, so you have 3 methyl groups hanging off the side, and that gives you soman. It's pretty similar. Its physical properties, again, are very similar. It's going to be more volatile than taubeun, but less volatile than cyclosarin, or less volatile than sarin, excuse me. So soman is actually the second most volatile agent, about 4,000 milligrams per cubic meter, thereabouts. Soman's properties are pretty similar to the other guys, kind of a fruity odor, onset's going to be pretty quick, and its lethal concentration and lethal dose 50 is fairly similar to the other guys, more or less. And then the last agent I'm not going to actually show you, but basically you have this nucleus is intact, and you have a long carbon-hydrogen chain that comes off with several methyl groups, and that is, of course, the VX. And VX is actually much heavier. It's about 270 grams per mole for its molecular weight, so pretty heavy, much heavier. Its volatility is only about 10, 11 milligrams per cubic meter, so it's not very volatile. So it's heavy, it's not very volatile. So it tends to be in a more liquid form. It's more persistent. It doesn't evaporate as quickly as the other guys. Therefore, it can stick around for quite a while, sometimes even several days if it's cool enough. The melting point of VX is about -51, so it's right around there about sarin. So it's easily, under normal environmental conditions, you'll find it a liquid. Its boiling point is about 300 Celsius. So you got to get it kind of hot to vaporize it if you're a weapon, and its volatility is really low. It's also highly toxic. Its LD and LCT50s are really low, much lower. You're looking at, from, I don't know, maybe 100. We were looking at its LD50, its LCT50, anywhere from 5 to 10. So it's much more potent than the other agents, but it's not as volatile, so it tends to stick around in a liquid, and it makes a really good area denial agent. Okay, guys, that's just a basic introduction to the molecular structure of the organic phosphorus agents. All right, I'll see you in the next video, and as always, thanks for hanging in there, guys.